All right, thank you, everyone. I hope you can hear me. I see head nodding and okay, fine. So I'm going to talk about a little bit about scheduling and how can we do kernel scheduling in Rust. It's kind of a tricky thing, but we can see if there's a way to do that. Well, I forgot. I work for NVIDIA, by the way. So I'm starting with the basics. I have some slides to just introduce about what is a scheduler, just to give some context. I don't want to go too deep into details, but scheduler seems really simple. If you think what the scheduler needs to do, it just needs to decide where a task needs to run, when, so there's an order if there are competing tasks to run, and for how long each task needs to run. So yeah, you have, usually you have multiple CPUs. There's a queue. You just distribute them on the CPUs that you have. Seems easy. Problem is you may have complex topology. For example, let's take into account caches or SMT. Like in this case, for example, we may have these big boxes around the CPUs. Might be like an SMT core, meaning that, for example, CPU 0 and CPU 1 share some resources. So if you send a task on CPU 0 and 1 at the same time, you may get a performance regression because they compete to use the same resources. So in this case, for example, a more efficient way of scheduling would be to send a task on CPU 0, let's say, the next one on CPU 2 instead of CPU 1, because you want to spread tasks and use different resources. On the other hand, if this is a cache, like the big box represents a cache, you may want to keep rescheduling the same task on the same cache because of cache locality, working set, yada, yada. You all know about that. Things can be even more complicated if you add NUMA into accounting. Like NUMA means that there are memory regions that are not, like the access time is not uniform. So if you are going to access a memory area in one place, it's faster. On a remote place, it's slow. The same happens, for example, with peripherals. You have a GPU, for example, or a network card. You want to keep tasks close to them so that you get better performance, better responsiveness, and whatnot. So yeah, for topology, things can be quite complicated. And so that's, for example, that's another example of a topology. So nowadays we have hybrid cores, meaning that not all the CPUs are identical, but you have like fast cores and slow cores. This is like, oh, who knows what kind of weird architecture is this one? Well, that's my laptop, not this one, but it's my other laptop. And as you can see, like fortunately, there's just a single NUMA node with a single L3 cache. But over there, you see here, there are, like these are SMT cores, so they share multiple resources. These are like regular cores. And actually, these are the slow cores. Those are the fast cores. So you may want to, what kind of decision you take in this context? You need to take into account like different CPU capacity, different locality, multiple caches. And so, yeah, things can get really complicated. What's the Linux approach to that? So the Linux philosophy is we must have just a single scheduler that works for everyone, so the one scheduler to rule them all. That's great because we don't want to have fragmentation. There is the concept of pluggable scheduling. That was proposed in the past, but it was rejected because the concern was two main concerns. One was performance. Adding callbacks and such into the scheduler could be a problem in terms of performance. The other concern was fragmentation. If you allow people to write their own scheduler, they may end up writing their own scheduler in-house, and they won't contribute any more upstream. So the idea was let's just have a single scheduler that needs to work in all the different cases that I mentioned earlier. But not only that, you may also have like different workloads. Let's say a video game workload is way different than an HPC workload. The single Linux scheduler needs to work for all these different workloads. And we used to have like CFS before version 6.6. Now we have eBPF. It's a different scheduler. It's designed, so CFS was purely based on vRuntime. It's a fair scheduler, like it tries to assign the same quota of CPUs across all the competing tasks. eBPF takes the same concept, but it's a deadline-based scheduler, so it's more oriented to like provide better response time, better latency, because that was one of the biggest complaints about Linux. Linux on gaming sucks because we used to have CFS. Now we have eBPF. Things should be a little better, but there are still problems. So one of the things is like, it's really difficult to conduct experiments because you need to patch the kernel, compile, install. If you have a bug, yeah, good luck. Test this in production. It's also difficult to upstream changes because, I mean, sometimes you find things that work really well for you, so you try to upstream them, and the maintainers are like, nope, we can't accept that because we're going to regress who knows who workload. Like we're going to make the database people unhappy. We're going to make the server people sad. So it's a very conservative community, understandably, because if you touch a tiny little line of code, you may end up doing like regressing a lot of other workloads. So how can we solve that, or at least try to address that? We have sched-ext nowadays. I'm one of the developers. Sched-ext it kind of take the same approach of pluggable scheduler, but approaching in a different way. It's actually a subsystem that allows you to implement your own scheduler, but in BPF. So we use the BPF. For those that the BPF environment, for those that are not familiar with BPF, how many of you knows what BPF is? Okay, yeah, good, almost everyone. It's basically a JIT in the kernel. So you can actually load at runtime some actual kernel code that is written in a BPF bytecode. It's interpreted at runtime. Performance-wise, is like loading a module. Same thing. You don't have performance regression for that. But you are limited. So you also have safety because you run kind of inside of a virtual machine in the kernel. So you can access in read-only mode things in the kernel. And you don't have, you can't trigger memory panic unless there's a bug in the BPF subsystem, but that's a different story. And you can't have memory bugs. Kind of Rust, but the thing in BPF is like there's a verifier, in-kernel verifier, that it doesn't even load your program if it detects that you may have a memory bug or an infinite loop or stuff like that in your code. So it's very safe to conduct experiments using BPF. And sched-ext is based on BPF. And so basically, long story short, you can implement your scheduler in BPF. So you have a safe way to conduct testing with the scheduler using this technology. We actually have a logo that I wanted to add recently. It's kind of an octopus. But anyway, sched-ext will be available in the kernel 6.12, is available as soon as it's released. One other important thing is one up here. So there's also a watchdog in the in-kernel subsystem of sched-ext that monitors like every task, that if a task doesn't run for a certain amount of time, it would automatically kick out your scheduler. So even if your scheduler is buggy from a logical perspective, like it's starving some tasks, you have a way to prevent starving your entire system. So worst case scenario that can happen, your scheduler will be just kicked out and the default scheduler comes in transparently. So it's safe. You can even test this in production. So that's how it works. There's an in-kernel part, and your BPF scheduler is basically implementing some callbacks. That's it. Like you have an enqueue callback when a task wants to run. You implement your own things. You have a dispatch when a CPU is ready to accept some tasks. So it's fairly trivial. But the cons are that due to the verifier that doesn't allow you to have infinite loops, it doesn't allow you to have potential memory bugs and whatnot, you're very limited. Like the BPF code, BPF language model is not a Turing complete, meaning that you can't implement everything. So you're quite limited. If you start to do complex things, you can't. Like and if you hit one of the verifier, I don't know how many of you have ever hit a verifier, BPF verifier error. It's kind of a pain because you never understand what's going on and why it's complaining. You're also limited in the stack, for example. Your arguments are limited. The number of instructions is also limited because the verifier needs to prevent having infinite loops. So it's great, but you're limited. So how can we overcome this limitation? Well, at some point I proposed this idea, like let's write, instead of writing a scheduler in BPF, let's write just a little layers, a little subsystem that doesn't do anything except for passing the event from BPF to a user space process. And then you're basically channeling the scheduling event to user space via BPF. So once you are in user space, cool, you're in user space. And there you can do whatever you want. You don't have the BPF limitations. You also have access to a lot of user space libraries that you can't use in the kernel. And you also have access to languages that you can't use in the kernel. So we are in a Rust conference. I was like, well, that's like slide 12. I haven't mentioned Rust yet. So yeah, that's the idea. Let's just use Rust in user space to implement one of the most important kernel functionality, the scheduler. It sounds crazy, but it's possible via sched-ext and BPF. So this is the design. This part is the same as before, right? There's the sched-ext in-kernel subsystem, the BPF scheduler. And at the moment, it's implemented using, so that's the idea, it's implemented using libBPF. libBPF RS is just a binding from Rust to BPF. We're actually planning to do some experiments with Aya. So replacing this part right here and this part right here with just one object. So it's going to be like BPF virtual machine and a Rust library and the user space scheduler that is going to be Rust. So right now, like the brownish boxes are like pure Rust code. So yeah, that's just, because that part requires Clang and C. So we're trying to make also this part in Rust if possible. So yeah, so as a proof of concept, I ended up writing this scheduler in this box right here. There is the scheduler, I call that rustland because it's like userland, but in Rust. It's just a deadline-based scheduler, nothing special, nothing fancy. Tasks use a variable time slice, and it prioritizes a lot tasks that are doing a lot of voluntary context switches. And I'll explain later why. Because my goal was to showcase a simple example, like just a simple workload, very specific. And I wanted to show, like, look, because the in-kernel scheduler is just one, and it needs to accept a lot of different compromises. I wanted to show how easy it is to beat the default scheduler if we can relax a lot of compromises. Because, you know, if you are, pretend to be the kernel, the scheduler maintainer, you can't accept any optimization if you're not like 100% sure that they're not going to regress someone else's workload. So if I have a way to load my own scheduler and unload when I'm done with my specific workload, super easy to beat the default scheduler. So that's why I wanted to prove this. I was expecting over it, because I'm passing, you know, through BPF and to use a space, so I wasn't expecting to get great performance, but I was saying, well, maybe if I can show like that I can be exactly as the default scheduler using this whole loop of events, that could be a, you know, cool thing to do. So I wrote the proof of concept and I tested it, and is it working? How much do you expect that I can do in a video game? I was expecting like 3 FPS or so, honestly. But after reiterating a little bit, it ended up being quite interesting. So I had this workload that is very special and probably not much realistic, but maybe it is. But basically, I was building the kernel while playing Terraria. Who knows Terraria? Who plays Terraria? You play. No, it's a great game. It's really good. It's also really good to do scheduling benchmarks because there are like multi-threads and it's quite simple. There is an in-game FPS counter in the bottom left. So while building the kernel, you can see that like I was doing like 26 FPS with the eBPF is the in-kernel scheduler, and with my user space Rust scheduler, I was actually doing 60 FPS while building the kernel. Maybe I can also show that. Like, okay, I prepare everything here. Let's see, let's try to build the kernel. Is there the game here? Yeah. Can you guys see? It's a little dark maybe. But yeah, you can see down in the bottom left, like I'm even doing like 20 FPS. It's very chunky, like it's really difficult to play. If I jump, it's like, ah. So let me go back here and start the rustland scheduler. Maybe if I type my password correctly. Ah. No? Doesn't like that?
The incident will be reported.
The incident will, yeah, I don't know.
Reported again.
Yeah, I think I messed it up, but so sometimes there is for some reasons it doesn't accept the password, and I need to restart the session. Ah, dang it. Okay, I think if someone wants to see that, I can show you later. I tried, but apparently, let me see if it's caps lock. No, okay, now I have the caps lock. Ah, bummer, that was cool to show the okay, whatever. I can show you later. If you grab me later, I'll restart my session. And okay, but yeah. So why it's happening, right? Because the reason is that so on the top part, you can see like there are lots. So this is Perfetto. It's a great tool developed by Google. And you can collect some traces and plot them to see like scheduling events. And you can, maybe you can't read, but these are all Clang that are built in the kernel. What the scheduler, the in-kernel scheduler is trying to do is trying to be fair. So Clang, all the ton of different Clang processes are getting the same bandwidth of Terraria. And like the main thread of Terraria is getting like a little chunks on one CPU, And it's basically surrounded by all these clang that are competing to use the CPUs. So the end result is that the compositor can't keep up at drawing the frames on the video, and you end up getting low FPS performance. Down here, because if you remember like a few slides ago, I'm saying that I'm prioritizing a lot of tasks that are doing a lot of voluntary context switches. And so the main thread of Terraria is doing a lot of voluntary context switches because it's, games works in pipelines. So they receive a frame, they process the frame, they pass the frame to another task. The task does some scene processing, passes the result to another task. So everything is a pipeline. And when you have pipelines, or when you have I/O, you end up working in a producer-consumer way, and you release the CPU before your time slice expires. So by prioritizing those tasks, by prioritizing pipeline chains and tasks that are voluntarily released in the CPU, you end up with this result like here. So you see that down here, the main thread of Terraria is jumping across the CPUs, but just because the system is massively overloaded. But if you squash everything together in a single timeline, you can see that Terraria is basically running all the time, despite all the other tasks that are running. So this is not fair at all. If I use this scheduler in many other contexts, this is not going to perform really well because of this unfairness. But in this case, I don't care because I wanted to optimize this very specific scenario. And that's why I get, the 60 FPS here. So yeah, that's what I was explaining, I was trying to explain, because games in general, they work in a pipeline. So you have a main thread that is waiting for the next frame. Usually you start processing a frame in a timer, with a timer, because 60 FPS, you have every 1 over 60 is 16 milliseconds. Every 16 milliseconds, the main thread needs to do something. So it's waiting. When it receives a frame, then it needs to process a scene, and then it releases the CPU, it passes the scene to another task that is usually something that renders, I don't know, the graphic and moves all the monsters and characters in the game. And then it passes everything to the compositor, and you go back to the beginning. So in this whole process, you have multiple threads, and they keep releasing and waiting and waking up others. So that's why that simple heuristic works in this case. And so this is the same scenario, but in an idle system. So my PC is only running Terraria. And you see, if you look at these greenish boxes, it's they're very, very periodic, very regular. Like every 16 milliseconds, that is exactly the 60 FPS, they're doing something. So that's actually Wayland. And Wayland is my compositor, so the one that draws every frame. And when it needs to run, it needs to run, or otherwise I would lose frames. And in this case, you see these Terraria has all these different threads, and they all, as you can see here, probably here, this is waking up another, this one is waking up this one is waking up the compositor. And that's the main thread. Again, there's another thread, who knows, this is a bunch of threads that periodically, maybe they process the scene, and then they wake up the compositor again. So in this scenario, the simple heuristic of either prioritizing the voluntary context switches or detecting, keeping track of the frequency of wait and wake up events per task is really effective. So yeah, that was cool. It was a cool experiment to show. But then I was like, okay, let's exploit the fact that we are basically in Rust, and let's try to provide some abstractions to this framework. So I basically extracted the logic of the scheduler and the backend of the scheduler into separate projects. And I created a crate that is called sched-ext rustland core that allows you to, it's the backend of rustland. So it provides you an API that you can use in a regular Rust project to design your own scheduler and run it. And then you don't have to understand all the BPF details, how sched-ext works. You don't even need to understand how the kernel works in terms of scheduling. And just need the API is really simple in this case because it's like it's very abstracted. And Rust helps a lot on this. Because you can just import the crate in your project. You cargo in it, you import your crate, you implement the scheduler, and it's done. And that's the design. It's pretty much the same as the other one. The only difference is that there's a rustland core here in the Rust code, and the rustland core in the backend that implements the BPF part. That's the only difference. And this was to prove that it's fairly easy to implement. So this is a fully working kernel scheduler that fits in a slide. That's pretty cool. It's a FIFO scheduler. It doesn't do anything special. But you see it's really difficult. It's really simple it's not difficult at all, I wanted to say. You have a main loop. You call the dequeue task to accept the tasks that want to run. And then you create a dispatch task, select a CPU for the task, you choose for how long it needs to run with the slice nanoseconds. Then you dispatch the task, and the backend will do all the job of interacting with BPF, channeling events, and whatnot. And you will end up having your task run on the target CPU for the amount of time that you have specified. That's so at some point. So I wrote this one, and I was like, I want to show that it's really easy to implement schedulers in Rust using this framework. So I had this idea to plug ChatGPT and take the FIFO scheduler in the slide before. I passed that to ChatGPT and I asked okay, now assuming this is the API, this is the framework. Please write a scheduler that is deadline-based instead of a FIFO. And that worked, and I made the video. If you go on this link, you can see that I'm asking in a human language, very high human language way, literally saying, modify this FIFO scheduler to have a variable time slice. Assuming this is the framework that you need to know, that there's a document, that there are comments in the FIFO example. And I wrote a little program that downloads the output from ChatGPT, compiles the code, and actually run that. So you can see me that I'm running a perf benchmark while ChatGPT is improving my scheduler based on my human feedback. So that's not, I don't want to say we're far from AI generating proper scheduling. In fact, this doesn't work if I try to tell the more complicated requirements, it just fails. But it was a way to prove that it's really easy to use this framework. to generate. I mean, it makes scheduling development accessible, can lower the barrier for scheduling development, while before it was very restricted to a few kernel developers with like many years of experience. Here, you don't have to understand much about I mean, you can understand scheduling in general, and you're good to go. So conclusion. Is rustland a better scheduler? No, definitely not. It works for that specific workload, for that specific scenario. Actually, it ended up really working really well for database for some reasons. I ran the 4onix benchmark, and you can see that like the Postgres latency time for read and writes is improved by 30% plus compared to the default scheduler. But just because of that heuristic that is over-prioritizing the voluntary context switches. And because the benchmark is just doing, generating SQL requests to the server and waiting for a response. So it's the same pipeline way that happens in the game. That's the reason. But in general, I'm not recommending to run this scheduler in general in production. But for specific workloads, it can work. The other thing is like, so when I posted the result, it was like an article on 4onix, like Rust makes gaming on Linux a great success. No, it's not Rust. I mean, it's the scheduler. Rust helps to make scheduling development and testing easier because of the whole abstraction. And then you have, like, if you have a scheduler in Rust, you have the memory safety and all the advantages that Rust provides. And you are in user space, so you can just, import, use crates from crates.io and do all the fancy things, reusing other libraries or somebody else's code. That is something that you can't usually do in the kernel because you are in the kernel. So you are constrained to the C code and the kernel requirements and whatnot. So the key point is really this one, in my opinion, is the fact that if the password was working for some reason, I could show you like that I can load and unload the scheduler simply by sudo running the command. If I Control-C, I go back to the in-kernel scheduler. So this part is really powerful, because if you have some experience with kernel development, like this is something that was really missing. And the other part is important as well, like integration with user space component. You can use, being able to use user space libraries is very powerful. So yeah, so future idea could be like, why don't we do the same? Why don't we follow the same approach for other subsystems, not just the scheduler? For drivers, for example, or file systems. You can have like a BPF, a tiny BPF layer that bounces the events from kernel to user space, and then you can implement your file system in Rust in user space, maybe. It's kind of a, the feeling is kind of a microkernel mood. So was Andrew Tannenbaum right at the end? Who knows? But at that time, we didn't have BPF. So baby BPF is the message passing interface in the kernel that we needed to make this possible. I mean, this is like future ideas in 30 years. Who knows when it's going to happen and if it's going to happen. But that's some ideas to think about it. I added some references to the project and questions. Yes, thank you.
Are there any questions?
Yes, there.
Hello. So my question might be pretty stupid, but I ask it anyway. So who basically decides which schedule will be run? Is it the administrator, or is it an application, which then concurrence with other schedulers, with other application schedulers? Well, who's behind that?
Yes. So well, you can do whatever you want at the end. Like from a sched-ext perspective, you have a user space process. So if you sudo / your process, you have the new scheduler. If you stop the process, you're going back to the default scheduler. So what we're trying to do in sched-ext, we recently introduced a concept of loader. It's basically a meta scheduler that the idea was to have like a config file where you can specify the different binaries that are the schedulers that are supported with options, and have profiles, like you have a low latency profile, a server profile, gaming profile, and based on dbus messages, you can say, okay, now, in perspective, it would be cool to have a way integrated with the desktop environment, saying like, I start Steam, and automatically via dbus, I send a message to the loader, and the sched-ext loader will load rustland, for example. And then the game is fine even if I start a kernel build in the background, or even if even if there's a big update run in the background, I can still have like a stable, solid 60 FPS. Or, I don't know, I start YouTube, and then there's another scheduler that prioritizes like multimedia workload, something like that. So the work is still a work in progress. I mean, sched-ext is a fairly new project. And everything around it needs to be designed and done. But that's how things are moving, yes, in this direction.
Having the scheduler in user space makes me worried. What if the scheduler is not going to schedule the scheduler? And so,
no, that's
I'm sure you have thought about it, and there should be some kind of safeguard.
Yeah.
But then there is another related question. Since we actually do have the possibility of running Rust in the kernel, would it be thinkable to overcome this kind of problem to put a Rust-written scheduler in a kernel module that uses exactly the same logical interface, but with the advantage that the scheduler code is in kernel? The same, so you should experiment in user space and then compile the kernel module and load the module. You got the idea.
Yeah, they're all valid points. So for the first part, like the scheduler is a user space process. So if a user space process is blocked, let's say on a page fault, yeah, so to resolve the page fault, you need to schedule a kernel thread. But the kernel thread can't go because the scheduler is blocked, so you have a deadlock. That was one of the biggest problems that I had to overcome in the project. At the end, I ended up doing like pre-allocating a memory area, M-locking everything, so the scheduler will never page fault. And in this way, everything works. It was tricky, but it works. The other part about using Rust in the kernel. So yes, we have Rust for Linux now. So there is the possibility to actually use like native Rust code in the kernel. It's doable. The only problem is the same as BPF. Like, you're kind of limited at the moment because you can't use everything that Rust provides in the kernel. There are limitations. And there's also the fact that you're missing a lot of abstractions. So it's doable. And there's another thing, like the memory model is different, especially in terms of reordering instructions. So if you're using spin locks or C in kernel structures, it can be tricky to make sure that Rust doesn't mess around with reordering pointers. And so it's doable. We will end up going in that direction. And it's also doable to say, like, OK, I prototype something in user space. If it works, I re-implement that in the kernel. That's one of the things that, like, one of the key point of sched-ext. Like, you can use this technology to prototype things. Because sometimes you may want to test stupid things, right? And they work. But then you need to understand why they work. But if you don't have a way to test that, I mean, this can give you a way to test also stupid things without messing up everything.
Thanks. Any other question? OK. So I didn't get the first part of the talk. Might be a stupid question. Who is deciding to install the scheduler? Like Steam, is this Steam installing the scheduler for taking advantage?
It's okay. So with sched-ext, you can implement schedulers as BPF programs. So you just need to load a BPF program. That basically means starting a user space task. You know, it's sudo /something, and you have a new scheduler in the kernel. Just you can dynamically load that at runtime without rebooting. So who decides which scheduler needs to run? It depends. I mean, it can be the user itself that runs the programs, or it can be like a manager. Like I mentioned earlier, we are working on it's called sched-ext loader. We're working on a meta scheduler that accepts messages via dbus. And you can send a message like load a gaming scheduler, and the manager will load a gaming scheduler. So in perspective, I was saying it would be nice to have like Steam. You start Steam. Steam sends a message via dbus to the loader. The loader loads a scheduler that is optimized for gaming, let's say. And then you have a Linux system that maybe works better for gaming. Then you're done with your game. You stop the game, close Steam. You go back to the default scheduler. And that's how we will probably end up being like in the future once we have all the pieces in place. Yeah. So, but the thing is like, yeah, the thing is like specialization, having schedulers, multiple schedulers specialized to do just one thing, but in a really good way, instead of having like a single scheduler that tries to do everything.
Yeah, I was just wondering if different programs comes with their scheduler and then they start competing again.
They compete each other. Yeah, so we are also working on a way to inside sched-ext to be able to load multiple schedulers and attach them to a C group. Like if you have, you know, it seems crazy, but if you're like running if you're a cloud provider and you run multiple virtual machines in different, or not virtual machine, multiple containers, right, that are doing different things, you may want to attach a scheduler to a C group or another scheduler to another C group. That's something we're working on. Right now, you can do that, because in your scheduler, you can say, you can resolve the C group and do different things based on the C group. So you can already do that. But right now, you can't load multiple schedulers. But yeah.
Thank you.
Yeah, so what is the BPF overhead?
So the BPF overhead is basically 0. Yeah, because if you think about that, it's just a just-in-time compiled code. It's like, it's kind of JavaScript for the kernel. It sounds bad, but it is really dead. Like it's bytecode, but it's dynamically translated. Really, like all the benchmarks that we have done, we haven't been able to like measure a perceptible overhead by using BPF. Especially in the scheduler, because if you think about that, the scheduler doesn't need to do a lot. It just, periodically most of the time there is the task time slice. And at the beginning and at the end of the time slice, there's just a tiny little time gap that the scheduler needs to do something.
Yeah, I just think you mentioned initially that it is an issue, but it isn't.
If you think like the networking guys, they're doing a lot of BPF, like all the packet processing and IP filters, IP tables, everything nowadays run in BPF. So even in that case, like the overhead is, we are basically running in kernel space, because most of the time the overhead is not about code execution, it's more about memory copy. That's the whole point, of zero copy and RDMA and stuff like that. So with BPF, you are already inside the kernel and you can access kernel memory area. You don't have to copy them to user space. So yeah, the overhead is, in general, it's minimal. Then maybe there is a case where like you're CPU bound and you can perceive the overhead introduced by BPF.
Yeah, thank you. And one more question. Any context on the other platforms like Windows and Mac? Like, does it simply work like that? Or?
Yeah, so Windows supports BPF. So in theory, I mean, that's like a very future project. Who knows when it's going to happen? But in theory, if there's a way like to have a compatible interface, we may have the same code running on the same BPF code running on Windows or Linux or potentially other kernels. Because actually, BPF now is a standard. There's a IEEE something or ITF, I don't remember. But it's standardized. So if kernels can implement their own scheduler machine, and the instruction set has been standardized, so potentially we have like a standard now, and kernels can implement the BPF machine. Of course, the problem is like the kernel interface that is going to be different, like the kernel ABI is different, but technically you can run the same BPF code almost everywhere if the kernel supports BPF.
Okay, thank you very much. Amazing talk.
Thank you.
Okay, any other question? Okay, come back to you.
So, how much should I worry about ruining my expensive machine like that? Like I don't know. This is just by ignorance. How much a scheduler can impact, I don't know, CPU temperature because maybe I just push to the limit one core and not the other. Can I be safe to experiment, or should I care about not blowing everything up?
So if you're in a desktop, you're pretty much safe. Like, yeah, unless, I mean, if you design your own scheduler, then you may have, well, you can do like, you can set the CPU frequency to go all its performance, and you end up like using more battery, but you're not going to burn your CPU, let's say, because the hardware then comes in and throttle. There's a thermal throttling and whatnot. If you try to do, like if you have a bug and you have starvation, there's no problem because the sched-ext in kernel watchdog will detect that and kick out your scheduler. So in a desktop environment, there's no risk whatsoever. The only thing is like if you run on a large NUMA system, you may have some issues because there's actually a bug that we found recently. I was also able to reproduce that on a very large machine with like, there's like 96 cores and 8 GPUs and stuff like that. Yeah, but because the problem is that, so internally in the kernel code of sched-ext, we have this concept of DS queues, dispatch queues, and they're global. They're not spread across multiple nodes, NUMA nodes, for example. So if your user space scheduler is hammering a DS queue from multiple NUMA nodes or multiple caches, you're kind of stressing the CPUs. And we found actually that it's possible to lock up, select soft lock up the machine by stressing a single DS queue running task from multiple NUMA nodes because the cache coherency protocol of CPUs are just hammering everything. But that happens only on Intel. On AMD, we're not able to reproduce the problem on AMD. But probably because like the Intel cache coherency protocol is more, I don't know, there's more overhead or we don't know what. But yeah, that's also another problem. But we have a workaround for that. Your scheduler will be kicked if this behavior is detected. So in general, yes, there's nothing to be worried about, unless you hit a bug. But
okay, there was a question.
yeah.
So the architecture of your scheduler here you presented is that you have a BPF program and then it communicates with your user space scheduler through ring buffers, right?
Yeah. I'm using the type ring map ring buffer and the user ring buffer.
Would it be possible to write a scheduler which is tiny enough that it's a self-contained BPF program and doesn't communicate with user space at all, or?
Yes. So this is called rustland, right? I actually re-implemented rustland in BPF, and I called BPFland.
Nice.
Well, yeah, a lot of that was predictable. No, but it works much better because there's no. I mean, even if you use ring buffer, the overhead is really minimal, but there is still some overhead. At the end, it's not about the overhead. It's more about, if you are in BPF, you have visibility of many kernel things, especially CPU masks. You can create domains using CPU masks, and because you are in kernel code, basically, in kernel space. In user space, one thing that is lacking in Rustland core is the possibility to create CPU masks and pass them to BPF or access them from user space to BPF in a safe way, meaning in a non-concurrency way. Because right now it's like if you do that, it's kind of a racy, like to detect idle CPUs. You don't have, like you set a bit in a CPU mask and you don't see instantaneously the same change in user space. So that's a problem that as soon as I get some time, I'm going to work on this and solve this. But right now, that's why BPFland is massively outperforming Rustland. And that's surprising, because like Rustland was already pretty good for gaming. So that's why like BPFland is now some distros, like one distro is called CacheOS. It's really cool, actually. They ship a sched-ext kernel. And the default scheduler is actually BPFland. So if you install CacheOS, you get BPFland. And it works really well for gaming. So yeah, it's doable. You can do that purely in BPF without doing anything in user space.
All right, thank you.
Okay. One last question. There was one. Yeah.
I have a couple of questions. You already answered to the previous one, guys before, that asked the overhead cost of the BPF. I just want to extend the question, if you have the chance to measure the overhead of all the tiny library that you need to put between the kernel and the user space scheduler. And the other question is, now that it's possible to run Rust in kernel space, if you think that it would be possible in the future to run the user space scheduler running directly in a user space without to get rid of BPF in general. For that.
Okay, so
now that Rust is partially verified, we don't need the verification of BPF, basically.
I see what you mean. Like,
yeah.
Why don't you have like user space and kernel without the BPF part?
Yes.
Right? Yeah, that's possible. BPF in this case doesn't give you much benefit in terms of verification because Rust already does what BPF does. That's true. The thing is, like, the fact that we have this channeling infrastructure, and if we don't use BPF, we need to write our own channeling infrastructure. Yes. So we will end up re-implementing a message passing interface from user space to kernel. That's possible, but it's work to do. It's what, like, so there was a few years ago, there was a project in Google called Ghost. It was exactly that, like the scheduling in user space, using not BPF, but their own way of message passing from user space, kernel in user space. And now they are reworking Ghost to be based on sched-ext, just because you have that way of doing message passing. So even if BPF doesn't give you much benefit, since you are in Rust already, it's still convenient because it's done and it's there.
Yeah.
And what was the other question about?
No, in terms of performance.
Performance.
The overhead of the tiny layer in
all
between.
the layers. Yeah, so there is overhead, of course, and so if I plot the same perfecto trace that I showed earlier, and you really zoom in, you see that there are like tiny little gaps between a task and another. That's the overhead. But that's the overhead because it's more because of how the scheduler is designed that is not perfectly work conserving. It's non-work conserving, so it tries to buffer a little bit some tasks so that it can do the reordering using the VRun time and the context switches. Because if you dispatch them immediately, you don't get much the benefit of doing the ordering, right? So that's the reason of the overhead. Because funny enough, if you run this scheduler here, I showed the scheduler in one slide, this one. If you run this, that is user space, right?
Yeah.
And you run there is the equivalent in eBPF that is called sched-ext simple. Is exactly the same. This one in user space performs better than the one in eBPF. And you're like, how is it possible? I mean, you have the overhead of all those libraries. But the thing is, like, it's really difficult to compare the schedulers because the scheduler doesn't do much at the end. It's just, it runs for a short amount of time to pick the next task. So this is probably performing a little better just because it gives some breadth to release the CPU. So the CPUs can actually, it's very, there are some coincidences and that sometimes are affecting the performance. And so performance-wise, this thing is performing almost exactly as or even better in some cases, as the eBPF one. So the overhead is very minimal. Because at the end, you don't pass much data between kernel and user space. It's just the PID and a few information about the task.
Okay, we're out of time. Sorry.
Yeah, sorry.
So that's it.